Hello. So we're going to start today's video with this picture. So what on earth could this be a picture of? What data could have generated this? Think about that for a minute. Is that temperature? What is that? Well, it's stratospheric ozone. In the 80s, they discovered a hole in the ozone, and it was alarming because you remember what stratospheric ozone does? It protects the Earth uh, from ultraviolet rays that would otherwise cause cancer and all sorts of problems. So when they discovered this in the 80s, it was a dire situation. But the world came together, and we're going to find out. So how does stratospheric ozone depletion happen? Well, this is a chemical called chlorofluorocarbons, CFCs, and we don't use them hardly anymore at all, but we used to use them a lot for propellant and for refrigerant. Now, the reason why I would use such a crazy molecule for a propellant is you can't just pack air in something like Cheese Whiz because the air's got oxygen in it and the oxygen is going to make things spoil. So chlorofluorocarbon was really stable, doesn't react with hardly anything, and it's non-toxic. So it was a perfect molecule to use. So they used it for putting in aerosol cans. You could put it in food products, like I said, with spray oils or cheese or something like that. And they also used it as a refrigerant, but it leaked out as a refrigerant when people threw away their refrigerators, and obviously came out of cans. And even though it was very stable at the troposphere, one thing they didn't realize was that in the stratosphere it wasn't so stable. In the stratosphere, that molecule, which is one carbon with two fluorines and two chlorines around it, one of the chlorines would become detached with the ultraviolet light. So now we've got this free chlorine. Well, chlorine is a very, very reactive molecule, and it's going to break. It broke off from the chlorofluorocarbon. But what that chlorine can do is going to react with ozone. And when it reacts with ozone, guess what? It's going to degrade it into O2. So it grabs one of the oxygens off of ozone and turns it into oxygen, destroying the ozone. So that's a problem. But that's just one molecule. But let's carry this out just a little bit further, right? Because this chlorine with the oxygen attached will find another oxygen and let it go. So it kind of acts as a little catalyst to bind two oxygen atoms. But now look at this equation. You start with chlorine and you end with chlorine. So what is possible now is that chlorine can just go ahead and do that reaction all over again. And so one chlorofluorocarbon molecule can end up destroying millions of ozone molecules. And that's the big problem. Chlorine acts as a catalyst in this case. That's a problem. We have to feed. So that world realized that, boy, it was startling in the end of the 80s. I was in college at the time, and this was a big problem. They looked at the hole, and it was getting larger and larger and larger. The purple there doesn't maybe look that dramatic here, but look at the difference between 1980 and 1991. So the world came together, and they drafted the Montreal Protocol on substances that deplete the ozone layer. The industry was not for this. I remember specifically the styrofoam industry was up in arms, and they said, if you get rid of CFCs, the styrofoam industry will collapse. Woohoo! Big problem there, right? But guess what? The styrofoam industry didn't collapse. They ended up being able to use air instead of CFCs, actually ended up being cheaper. So whenever you hear corporations and companies, factories saying they can't do something, well, when they're forced to do something, sometimes they can do it. So this is the Montreal Protocol. It was designed to reduce the production and consumption of ozone-depleting substances in order to reduce their abundance in the atmosphere, thereby protecting the Earth's fragile ozone layer. And they did this mainly in the United States anyway, by taxing chlorofluorocarbons so high that they prohibited their use. And I think now they're just about outlawed. So chlorofluorocarbons, no more used. And so that's an excellent thing. That was one of the most successful environmental treaties ever. It's a great example of when the world had to act, it did. So we can do the right thing at times, even when it's against what companies want. Here's a quick little movie that explains it a little more visually.
The stratospheric ozone layer, so important to life on Earth, can be depleted by catalytic chemical processes. In recent years, man-made chemicals have contributed to the loss of stratospheric ozone. Among the most important of these are chlorofluorocarbons, or freons. For example, Freon 12. Chlorofluorocarbons, or CFCs, are very stable molecules in the lower atmosphere. Over a period of years, they slowly diffuse into the stratosphere. In the stratosphere, the CFCs are subjected to energetic ultraviolet rays that can cause rupture of the carbon-chlorine bond. The chlorine atoms act as a catalyst for the decomposition of ozone. Collision with an ozone molecule results in oxygen transfer, forming ClO and molecular oxygen. The ClO that is formed reacts with various species, notably atomic oxygen, to reform the chlorine atom and producing molecular oxygen. The sequence of reactions consists first of reaction of chlorine atoms with ozone, followed by the reaction of ClO with atomic oxygen. The overall reaction is just the decomposition of ozone. Atomic chlorine acts as a catalyst for the decomposition. Because the presence of CFCs in the stratosphere is capable of substantially reducing the ozone shield on which life depends, their manufacture and use has been greatly curtailed in the industrialized nations. Nevertheless, their effects on the ozone layer will remain for decades.
So notice that in the reaction, the catalyst isn't even in the reaction. Oftentimes you write the catalyst on the top of the arrow. That's just the way it goes. So stratospheric ozone depletion is caused by CFCs, or you can call them CF2, CL2, chlorofluorocarbon. But the brand name that a lot of people know is Freon. So Freon is just another brand. It's a brand name for CFCs. There are some alternatives. So we needed to learn to make alternatives. I already told you they use air to make styrofoam now. But for a refrigerant is a complicated substance. And so there are some alternatives to Freon. And I put this periodic table up here because if you see where chlorine is, it's right next to fluorine. And so bromine, not fluorine, but bromine. Bromine is another compound. So chlorine and bromine compounds are often used as refrigerants. And so they made these new hydrochlorofluorocarbons and hydrobromofluorocarbons. These HCFCs and HBFCs are more commonly used now as a refrigerant. The problem with these is they don't go up into the atmosphere and eat don't eat ozone, but they are you got cut off there, but they're very powerful greenhouse gases. So we've kind of traded the destruction of the ozone with now putting in a greenhouse gas. One thing that you need to remember is that a lot of people think about the destruction of the ozone layer and that's causing climate change. There's no connection in there. Ozone actually is a heat-trapping molecule, but the destruction of the ozone is bad for life on Earth because of ultraviolet radiation coming in, not because it increases climate change. What increases climate change are the alternatives to chlorofluorocarbons. And so there's going to be a big future in creating refrigerants that do not use these hydrochlorofluorocarbons and hydrobromofluorocarbons. So review that if you need to. Know the chemical equations. You can now try that practice ozone sheet, and you should review the creation of stratospheric ozone and the creation of tropospheric ozone as well. You're going to need to do that a couple times before you get the hang of it. And of course, if any of this is confusing, I will help you personally. I've got a whiteboard here, and we can do it during office hours so that you understand this well. All right. See you soon.